Hello, today I will be talking about lab experiment number 3. First of all, it is important to understand the purpose of this experiment, which is how to calculate the mass of an unknown black hole given the trajectory of a given star orbiting around it. The predicted results are that knowing the critical information about the object revolving around the black hole, like its speed, mass, and initial position, are fundamental into calculating the gravitational interaction that occurs between the black hole and the star, and therefore be able to calculate the mass of the unknown black hole. These calculations are done by setting the initial conditions in VPython, and then by running the code, we see that we are doing the reverse process of the calculation of the predicted motion of a star around the black hole. The final printed result we will obtain is the mass of a black hole that affects the motion of a star. For overview of the experiment, we know that the system is a star orbiting around the black hole. The surrounding is a black hole that exerts the net force over the star, and we know that we need to understand the fundamental physics principles, which is the momentum principle, which is delta p over delta t equals F net, and Newton's second law of gravitation, which is Fg equals g times m1 times m2 over magnitude of r squared. Then we know that the obtained data, which is that the star mass is 1.989 times 10 to the 30 kilograms, which is also called mass 1. We know that the time step, which will be the delta t, is at 86,400 seconds, which is 1 day. And also we know that the initial black hole position, the star initial position, and the star final position. We also know that the g component is 6.7 times e to the negative 11. For the process of making this video, we need to understand that the components of delta p over delta t are dp dt parallel and dp dt perpendicular. This is equal to the magnitude of the delta p times the p hat plus the magnitude of p times the delta p hat. So the parallel component describes how the star speeds up or slows down, and the perpendicular component describes how the star curves and how the trajectory changes. For the calculation of the black hole mass, we have this new equation, which is equal to BHM equals F net times R, or R squared, which is the radius, over G times M1, where F net equals delta P over delta T, R equals radius, and M1 is the mass of the star. So, for our Python code, we need to set our initial conditions. We already know the star mass, which is this one, the delta T, which is this one, and we calculate the velocity. The process of this model calculates the velocity by itself. Um, then we also need to put in some other conditions, which is P initial equals star mass times V initial, and P final equals star mass times V final. This is how the model will calculate the velocity. Also, we need to put some other calculations, which is the F net equals dp dt and the parallel and perpendicular components of dp dt, which is dp dt parallel equals d mag p dt times p hat, and dp dt perpendicular, which is dp dt minus dp dt parallel. After knowing this, we know that F net perpendicular equals dp dt perpendicular and F net parallel equals dp dt parallel. Also, at the end, we need to set our arrow scale to this value that we obtained by some calculations, and also by the index, we calculate g, the black hole mass, by using the equation we used before. So now I'm going to run my code. While we're running this code, we can observe that the three arrows change depending on the direction of the dp/dt parallel and dp/dt perpendicular. We see that the yellow arrow will always point to the center of the black hole, and this represents the F net. Now, for the mass of the black hole is this value because we printed it in the BPython model. To answer the what does it mean question, it asks if F net parallel, and F net perpendicular are different from dp/dt and its components. We know that these represent the same magnitude, but the main difference is that the components of dp/dt describe changes in the motion of the star, and the components of fnet represent the interactions that affect the star's motion. To answer the what if question, Is it possible for you to find a value for the mass of the new black hole that is different from the mass you found for the original one? And the answer is that it is not possible for there to exist a new black hole with a different mass that does not change the trajectory of the star. If the new black hole was different, the star would experience a different Fnet, and therefore its motion would be affected. In conclusion, you can calculate the mass of an unknown black hole by knowing the initial conditions of the star and by observing its trajectory. The fundamental principles are accurately used in order to describe the motion of the star in parallel and perpendicular components, and thank you for watching.